So we talked about galaxies and collisions in star and galaxy clusters and how that can lead to elliptical galaxies and so forth. Well, question, where do the galaxies themselves come from? Because we know how stars form. How do galaxies form? Several ideas they've had. Big clouds of gas swirling together and makes a galaxy. Or gas comes together and makes several galaxies which merge to make a galaxy. Or some astronomers came with the idea that a whole bunch of little clumps came together, and as the clumps came together, they start swirling up and making a galaxy. So which of these is it? Well, to find out, what happened was, in the early days of the Hubble telescope, they just pointed the telescope in empty space. And they just pointed it in empty space and let it get a time exposure, for like a week or so at a place that they really didn't see much of anything that was there. And this is called the Hubble Deep Field. And so they pointed to a little patch of Hercules where there wasn't anything that was known to be there, and really, really long time exposure let them see things that are dimmer than they'd ever seen before. And so turns out most of what you see in this picture are galaxies. There's a few things here that are stars, but almost everything else is a galaxy. If you look at the very small background, what you see are a whole bunch of little small clumps of gas where stars are starting to form, and these things are clumping up to make bigger things. So it does look like galaxies start off as little clumps that clump up to make bigger things, which clump up to make even bigger things, which clump up to make galaxies. It's kind of very similar to the way we think planets form. So, next question is, when they clump up and we start forming galaxies, is it totally random? So we know galaxies form in clumps. Galaxies are often found in clusters. And so here is a map of 2 million galaxies. And you say, is it totally random? Well, if it's totally random, it's completely uniform. Well, we actually do notice there's places that are darker and places that are brighter. So it does indicate the galaxies clump up. So we do have galaxy clusters. But it's not just galaxy clusters. If the galaxy clusters were all uniform, this should still look pretty uniform in the entire sky. This suggests that clusters of galaxies also cluster up. So we have clusters of clusters. We call those superclusters. So superclusters are a cluster of galaxy clusters. So if we try to map all this out, 60,000 galaxies, we have several different superclusters. And so we name the superclusters by what part of the sky. So the Virgo supercluster, or the Virgo cluster here, is a giant cluster that the local group is associated with. We're orbiting around there. So the Virgo cluster, the center of what we call the Virgo supercluster. And the Virgo supercluster, since we're part of it, we also call the local supercluster. Well, it turns out the local supercluster and several other superclusters are all being pulled towards something that we can't really see because it's on the other side of the local supercluster. And so a fellow named Alan Dressler comes up with the idea of just calling this thing that we don't know what it is, that it's pulling everything together, the Great Attractor. So it does suggest there's larger structures perhaps in the universe. So we have superclusters here. We have a variety of superclusters. The Virgo supercluster, we have the PHYS supercluster, all these other superclusters that are out here. And so this raises another question, is that random? We have all these superclusters and we say, is this random or is there clumps of superclusters? Because it looks almost as if there's like empty spots in there. So the idea that there might be empty spots came from actually a fellow, Stephen Gregory, who discovered there are these large voids where you didn't seem to find very many superclusters. And so that led a graduate student by the name of John Huckra to suggest maybe there are supersized superclusters. When I was in graduate school, the term they were tossing around was superclusters. I always thought it should be called super duper clusters. But anyway, his professor was Margaret Geller, And he was studying this, and so the idea was, how do we? And so what happened was they just started mapping distances to superclusters, and they discovered that, and I guess it was actually an interesting thing. How does this work? Because it was trying to figure it out, and so what he discovers was that superclusters actually tend to fall not by themselves, but not really in clumps of superclusters. So no superclusters. Instead, the superclusters tend to all line up, forming giant walls of superclusters surrounding these voids. And so, because of his work, Margaret Geller got a rather substantial prize. Remember, graduate students don't typically get the prizes. So she got recognition for a graduate student discovering walls and voids. Okay. With that discovery, other studies have indicated, yes, indeed, there are walls and voids. The walls are in 3 dimensions all over the place surrounding empty voids. And what does that mean? That suggests that the universe actually is spongy. Where the solid part of the sponge would be like the walls of superclusters, and the empty regions are the voids between the superclusters. Now, the voids are not totally empty. They're just like much, much less dense than the rest of the universe. Now, the problem is they didn't think, the reason this was not originally thought to be a very good project for a graduate student was that the universe really isn't old enough to clump up this way. So that means there's something else going on. Again, we're back to dark matter. Universe is not quite old enough to really clump up in this fashion to make superclusters. So dark matter is helping it do that. And in fact, this actually constrains the type of dark matter that we have. This is what we call high energy or hot dark matter, which has to run back and forth between everything at close to the speed of light in order to carry the energy and arrange everything so gravity is able to do this. So again, computer simulations show that if you have enough matter and enough energetic matter, dark matter, that it will go from a uniform void, uniform sort of mass, into these clumps of filaments that give us these walls and voids of superclusters and voids. Okay, again, there's not enough known mass, so we have to have dark matter doing this. Well, it turns out, interestingly enough, the local group is right on the edge of a void. The void was discovered by Tully and Fisher in 1987. It's about 75 megaparsecs across. It's only 4 million light years from us. Remember, the local group's not all that big. The Andromeda Galaxy is about 2.5 million light years away. So the local void just comes right up to the edge of the local group. And so the local void has about 1% of the normal density of the rest of the universe. Voids are really interesting because it turns out that mass affects the expansion rate of the universe. So this does have interesting sort of properties to it. The reason the local void's hard to find is that the zone of avoidance stretches right across it. So that makes it very, very difficult to actually see the local void. So this, though, gives rise to our understanding. Earth. It's where we live. Earth is part of the solar system. It took a long time to realize that we're not the center of the universe, but Earth is part of the solar system. We go around the sun. The sun and the solar system is a group of stars here in 3 dimensions, but all of that is going around the center of the galaxy. And so our galaxy, the Milky Way galaxy, for a long time they thought that was the whole universe. And then they realized, oh no, wait a minute, the Andromeda galaxy. So we have this group of galaxies here. And then we realized, oh wait, we have all these other galaxies out there and they all clump up into a supercluster. And then we realized that the supercluster is just one of a whole bunch of superclusters. They started realizing that all these superclusters line up along walls and voids. And this gives us our understanding of the large-scale structure of the universe.